Swayam Prabha. Digital India. Educated India.
Welcome students. If you remember, in the last few classes we have been discussing the particle in a box problem. So far we have formulated the problem, we have seen how we could solve the particle in a box problem, and then we also have obtained the eigenvalues and eigenfunctions of the Hamiltonian operator for this system. We have also analyzed the eigenvalues, the energy spectrum, the different properties of the eigenfunctions, and we also looked at the average property or the expectation value of position operator. In today's class, we will continue our discussion and we will use the eigenfunctions that we have obtained to discover different properties of this system. The first thing that we are going to discuss today is the average value or the expectation value of momentum operator for this particle in a box problem. When I say expectation value, of course we know that we have to, so now we are going to discuss the expectation value of the momentum operator. So when I say expectation value of the momentum operator, I mean I have to evaluate the integral this is the operator form of the momentum operator, and these are the wave functions. The integration limit, as you remember, the particle can, the x axis is defined from minus infinite to plus infinite, but then we have also mentioned that between 0 and L the particle experiences 0 potential. Outside this box, particle experiences infinite potential. Outside the box, the wave function vanishes. So therefore our integration limit we can set as 0 to L. If you remember, the wave function, the functional form of the wave function was under square root 2 by L and a sine function. So I am first writing the normalization constant 2 by L under square root, but I have psi n star and psi n, so both combined, so therefore the square root is missing, and I have sine n pi x by L, and I have this operator minus I h bar d by dx, and I now have to solve this integral. I see 2 by L, and then I see that this minus I h bar I can bring out of the integration, and then I look at the integral. So I have a sine function here and a differentiation of a sine function with respect to x. When I differentiate this function, I have n pi by L which comes out, and I am left with a cosine function. Okay, so this constant I will bring out, and then I am left with a sine function and a cosine function. I can simplify these two functions by two sine theta cos theta as sine 2 theta, and when I integrate this function, finally I have these constants outside. So I'll bring them later. Let me see what I get here. In the limit 0 to L. So if you see, when I use x as L, so L cancel out, and I am left with cosine of 2 n pi, which is 1, and when I put x as 0, that also makes cos 0 as 1. So therefore this function turns out to be 0, and as a whole when I multiply this 0 with this constant, I get 0. What I see here that the expectation value of momentum operator is 0. As you already know from the results of the expectation value of position operator, the expectation value represents the average value of the momentum. Now, when I see an average value of 0 for linear momentum, this indicates that on average the particle actually has no speed or no momentum. So, as if the particle is static. This result also has a deeper meaning if we analyze it a little further. If you see this, the wave function that we had as the from the particle in a box problem, I am writing only the wave function without the normalization constant. This wave function is not an eigenfunction of momentum operator. So, if you remember, the momentum operator is minus I h bar d by dx. So, when I apply momentum operator on this eigenfunction, on this function, I get a cosine function. So, when I do not get back this function that I am acting on, so this is not an eigenfunction for this operator, that we already know. So, therefore, when I measure momentum, linear momentum for this state function, I am not going to have a definite value, rather I will have a linear a linear combination of several possible values. But I am going to rewrite this state function in a slightly different way. So, I would use sin n pi x divided by L. I can write it as e to the power I n pi x by L minus, sorry, this is plus I minus e to the power minus n pi x by L divided by 2I. So, this simply converts a sine function, expresses a sine function in terms of an two exponential function. Sin theta equals e to the power I theta minus e to the power minus I theta divided by 2I. Now, I see this wave function, this state function sin n pi x has two parts. One is e to the power plus I n pi x by L, another is e to the power minus I n pi x. If you observe carefully, these two exponential functions are actually eigenfunctions of the linear momentum operator, that we can show without any problem. So, I see I minus I h bar d by dx, this is the linear momentum operator, and when I apply it on I n pi x by L, what do I get? So, minus I h bar remain. When I differentiate this exponential function with respect to x, I get I n pi divided by L e to the power I n pi x by L. I can simplify it by minus I into I as plus 1. So, I have n h bar pi divided by L e to the power I n pi x by L. So, what I see here is that this function is actually an eigenfunction of this linear momentum operator with an eigenvalue of n h bar pi divided by L. I can also do the same thing for the other component e to the power minus I n pi x by L, and I would get the eigenvalue as now. When you look at this result, we see that all the sine function is actually not an eigenfunction of the linear momentum operator, but I can express this sine function in terms of two exponential functions, and each of these functions are actually eigenfunction of linear momentum operator. And what are the corresponding eigenvalues? So, when I have this function as an eigenfunction, the eigenvalue is n h bar pi divided by L, and when I have this as the eigenfunction, the eigenvalue is minus n h bar pi divided by L. Now, when you look at these two eigenvalues, they are simply negative of each other. What does that mean? That when I have the state function expressed in terms of a sine function, this has two components. One component is an eigenfunction of linear momentum operator with an eigenvalue, or the observable of the linear momentum or the linear momentum itself is plus n h bar pi divided by L, and the other component represents the negative of its negative of this eigenvalue. So, in other words, when I express the the particle in a box state function, it has got two components as eigenfunction of the linear momentum operator. One goes left hand side, another goes right hand side of the box. So, on average, when you take both the components, the average expectation value of the linear momentum turns out to be 0. So, the result that we saw, that if the expectation value of linear momentum operator for a particle in a box problem is 0, this makes perfect sense. Please note that the expectation value of this linear momentum operator for the particle in a box problem does not, the expectation value does not depend on which state function I am considering. Does not matter what value of n I am considering, the expectation value is always going to be 0. The way, just to remind you, in the similar way we also saw for the expectation value of the position operator, that does not matter which state function I am considering, whether n is 1 or n is 2 or n is 3 or n is 4, it does not matter. The expectation value of the position operator was always L by 2, and now we saw the expectation value of the linear momentum operator is always 0. So, it is very important to understand what the expectation value or the average value represent as opposed to the eigenvalue of a particular state. In the next, we actually would go beyond the particle in a box, and we would look at a particular solution, a particular problem which goes by the name free particle. What do we mean by free particle? If you remember, the particle in a box experienced 0 potential within the box, and outside the box it experienced infinite potential. But as a free particle, when we say free particle, we mean that the particle experiences no external potential whatsoever all through the space. So, in other words, I have, if this is my x axis, it goes from minus infinite to plus infinite over 0. So, the potential energy operator is 0 throughout. So, we said that potential energy is 0, the kinetic energy, so this is a free particle of mass m. So, the kinetic energy is minus a square by 2 m d square by dx square. So, again we are considering the movement of the particle along one dimension, only along one dimension. So, this is my kinetic energy, this is the potential energy. So, I can write down the Schrodinger equation as where the Hamiltonian is sum of kinetic energy plus potential energy, and the Schrodinger equation is H psi equals E psi. When I use this form of the operators, I see plus the potential energy is 0. So, therefore, the potential energy is 0, and then I have the right hand side E psi. I can rearrange this. We have already seen this equation a few times. So, I hope you are familiar with this equation by now. I rearrange this equation to write this homogeneous second order differential equation, and we in the previous classes we also have discussed the solution of this particular differential equation. So, the solution, if you remember, would be we will have two exponential functions, C1 e to the power e plus C2 e to the power minus I So, the general solution of this function is shown here. I have one exponential function with plus exponent, another with minus exponent. Now, this is the general solution. If you remember our discussion on particle in a box problem, from here we started and then we said that okay, we would impose some boundary condition in the particle in a box problem, because in a particle in a box problem we had the particle experiencing different potential at different region. So, at the interface of the two regions, if you remember, we called region 1 and region 2 and region 3, at the interface of region 1 and 2 and at the interface of regions 2 and 3, the wave function must be continuous. That was the boundary condition that we imposed for particle in a box problem. However, when we have a free particle, it experiences no potential all along at all values of x. So, therefore, there is no boundary condition that the kind of boundary condition that we saw in the previous problem is not there. But to have an acceptable wave function, we can impose one particular condition on this wave function, that this wave function should remain finite at all places. So, even when x goes to plus infinite or minus infinite, the wave function should not become infinite. So, the wave function should remain finite even when our variable x becomes plus infinite or minus infinite. So, this is the condition that we can impose on our problem. Alright. So, if we have this condition in mind, let us look at this solution little more. We continue our discussion in this here. So, suppose we consider a case where E is less than 0, that means negative values of energy. When I have E is less than equal to 0, then what happens to this value? Since E is negative, the negative quantity under square root will give me an imaginary root. So, I have E and I can write this as absolute value of E, because I have taken out the minus sign of the energy value when E is negative to the outside of the square root, and what I am left with is simply. So, for negative value of E, I can write down this wave function as something like this, e to the power. So, now, let us analyze these two functions. Suppose x goes to plus infinite. When x goes to plus infinite, you see, because what happens to this term, x is very large, but I have a negative sign here. So, therefore, this term becomes very small. So, when x goes to infinite, this term would tend to become 0, very small, it would go to 0. So, therefore, this does not create problem for me at x equals plus infinite. Let us look at this function. When x goes to plus infinite, this x becomes very large, and e to the power this large value becomes extremely large going towards infinite. So, when x goes to infinite, this particular term also becomes infinite. But we know that we have a condition to fulfill, that when x goes to infinite, the wave function should remain finite. To keep the wave function finite, we have to do something. What can we do about it? So, we have to say that this solution would not be acceptable at x equals plus infinite, and to do that we can simply say when x goes to infinite, C2 should become 0. So, if C2, the coefficient for this function is 0, so that means the contribution of this function is not there and we are happy. Let us look at the other end, when x goes to minus infinite. When x goes to minus infinite, let us first look at this term. When x is minus infinite, I have no problem here because this is x is minus. So, then the e to the power large minus quantity, so which will tend to go to 0, and this function is fine. This function will not become infinite at x equals minus infinite. Now let us look at the first function. The first function, when x equals minus infinite, will become e to the power a large positive quantity, which will become infinite when x goes to infinite. So therefore, at x equals minus infinite, I have problem with this term. So to solve this problem, I will have to impose a condition that C1 is 0 at x equals minus infinite. Now considering the fact that at plus infinite I should make C2 is 0, at minus infinite I must make C1 equals 0, since I have a free particle going from minus infinite to plus infinite, and I am going to get one state function for the entire system. So when I put C1 0, C2 0, the wave function itself becomes 0. So what it tells? So the wave function is 0, so therefore the probability density is 0, that means the particle does not exist. So what does not exist is that negative solution, negative value of energies are not allowed. So this gives us for free particle that only E greater than or equal to 0 values are allowed. The free particle cannot have negative energy. It can have any energy which is greater than or equal to 0. Now at this point we would spend some time in understanding the solutions that we obtain. So one particular condition, one particular thing that you should see, that when I put E greater than or equal to 0, the wave function is ensured that it will not become infinite at x equals plus infinite or minus infinite, because in that case it would become e to the power. So when E is positive or E is 0, so this quantity is real, overall this quantity is imaginary, and e to the power plus I theta or e to the power minus I theta can be expressed in terms of a cosine theta and sine theta term. And when I express something in cosine theta and sine theta term, the advantage is that the cosine function and sine function are bound between plus 1 or minus 1, so therefore they would never become infinite. So my wave function for E greater than or equal to 0 remains finite even at x goes to plus infinite or minus infinite. But this does not solve all my problems, because when the wave function is finite, even when x is infinite, that means that I can never integrate this function, or this function is not square integrable. So if I am not able to square integrate this function, that means I cannot normalize this function. If I cannot normalize this function, so C1 and C2 are hard to get. So the free particle solutions are, the allowed solutions are E greater than or equal to 0, and these functions are not normalizable. And they are also not quantized, because what so far we have no boundary condition that which existed like the way it existed in particle in a box that gave us a discrete solution. Here there is no such boundary condition to make the energy levels discrete. So therefore all positive energy values are allowed. So therefore they are not quantized and they are not normalizable. But if you remember our previous discussion, if the wave function is not normalizable, then we would not call it a well behaved function or an acceptable function. But this problem does not arise here, because strictly speaking there exists no free particle. You can never have a particle which is devoid of any interaction with everything else. It is an ideal problem. In reality, however, if you can get a somewhat a free particle, in that case you can normalize it within the experimental conditions. When I say free particle, it is perhaps important to give you some idea about what physical system can represent a free particle, then the answer to that question is that you have seen photoelectron experiment. So, when you shine irradiation on a system, then you eject a photoelectron. That photoelectron, which is now outside the influence of the molecular environment or the nuclear environment of the molecule, is an example of a free particle, is an example of this free particle. So, therefore, in such a case, when we have a free particle, although we cannot actually normalize this system, but still the solutions are there. So, in this class so far, what we have done is that we have discussed particle in a box problem and a free particle problem. In case of particle in a box problem, all our wave functions were bound solutions. For example, if you remember the solution of particle in a box problem, all our wave functions were bound. That means they were all present within the dimension of the box. But in case of a free particle, the free particle, since the allowed functions are all e greater than or equal to 0 and they are sum of a cosine and sine function, so they are found everywhere. So, they can be seen from minus infinite to plus infinite. So, therefore, they represent what we call unbound states. The free particle solutions are unbound states, whereas the particle in a one dimensional box solutions, they represented all bound state. In between the bound state and non-bound state problem, there exist the real systems. For example, it is very when we say that the particle experiences infinite potential, that means the molecule is extremely stable, the electron never leaves the molecule. When we say the free particle, that means the electron has already left the molecule. But most interesting part of the story lies in the intermediate case, where the particle or the electron experiences not infinite, rather a finite potential. If you remember all your chemical reactions that you have studied, when there is an electrophilic attack or a nucleophilic attack, when you have reactive molecules, that means the electrons are willing to come out of the nuclear environment and do the reactions, right. So, in those cases, the electrons do not experience infinite potential, nor do they experience no potential, rather they actually experience a finite potential. So, there exists methods to solve particle confined to a finite potential energy barrier. So, they are called particle in square well, but for this particular topic lies beyond the scope of our discussion. But when we take particle in a infinite potential or a free particle and particle in a finite wall, we actually cover the entire range of potentials that the electron can experience. Thank you very much.